All right, we're continuing our discussion on shear strength of soils, and today we're going to talk about the Traxel test, which is a very common test. We talked last time about the direct shear test, which is certainly one of the simplest tests to obtain the shear strength of soils. The Traxel test is more complicated, but it has many advantages over the direct shear test, one of which is that we're measuring deformation properties of the soil at the same time as we measure the strength of the soil. So again, our discussion or our topic is shear strength. And today we're going to talk about the Traxel test. So triaxial, three axes. Actually, there's really no two axes, but let's see how it works. Well, so we take a sample, and the sample is placed in a chamber, and it sits on a pedestal, and there's a chamber that covers the sample. So this is the soil sample right here, and we have a cap on top of the sample, and we apply, through a piston, we apply a load onto the sample. The first step is to apply a pressure, an all-around pressure, sigma 3, all the way around the sample, hydrostatic confining of the sample. And then we increase the load in the vertical direction, so we have Q, we apply a load Q divided by this area A here. That's the area, the cross-section area of the sample, and so Q over A is felt as well on this side, and the addition of Q over A and sigma 3, this becomes sigma 1. And you remember that there are stresses in any material, and that these stresses act on various planes. That whenever you talk about a stress, you have to define the plane. And there are planes that are such that the stress on that plane is only a normal stress, there's no shear, and that's the definition of the principal stress. So just as a reminder, principal stresses, normal stresses, on planes with zero shear stress. Okay? And it turns out that there are three of those. There are three such planes. So there are three such planes. And the stresses and the corresponding principal stresses will be sigma 1, or we'll start with the small one, sigma 3, sigma 2, and sigma 1. And these stresses act on three perpendicular planes. So if you consider a cube like this, you would have on that cube, you would have the minor principal stress, that's the smallest one, sigma 3. You would have an intermediate principal stress, a little bit larger, sigma 2, and then you'd have the big one, sigma 1. So these are three principal stresses on three perpendicular planes, and these stresses exist under our feet right here in the soil. If you pick a point, that point will be the stress field at that point will be characterized by three principal stresses. If you move to another point, you have another set of different principal stresses. So when we run this triaxial test, we apply sigma 3 in this direction, sigma 3 in this direction also because it's all the way around, and then we increase the stress in the vertical direction, and that becomes sigma 1 because it becomes the big one corresponding compared to sigma 3. So in the triaxial test, sigma 2 is equal to sigma 3. So it's a special case. Even though we call it triaxial test, sigma 2 and sigma 3 are equal to each other. The way we run the test is in two phases. So as I explained, we have a first phase where we apply this confining pressure, sigma 3, all the way around. Sigma 3, sigma 3, sigma 3, sigma 3. Okay? And we do that with air or water, or it depends on the system we use. But we apply this confinement. We call this the consolidation phase. Consolidation phase. And this consolidation phase, we can do it drained or undrained. Drain means that when we squeeze the sample, now usually we have a membrane here, but when we squeeze the sample with this sigma 3, we can let the water go out. So you might have, a pore right here, and then the water can actually squeeze out of the sample. But we also have a valve on that line, and we can close the valve, and that will lead to an undrained consolidation phase. Or we can open the valve, and then some water will drip out. We will call that a drained consolidation phase. So the consolidation phase can be drained or undrained. And the way we choose this is depending on the problem that we're facing. The drain, we will call it consolidated. And undrained, we will call it undrained. And we will use the letter C to characterize this choice, or the letter U to characterize this choice. First phase, all right, so this was phase 1 of the test. Phase 1. And we call, so this is the consolidation phase right here, all right? Second phase is the shearing phase. So phase 2. Phase 2, then in that case, we have the sample again, same sample. So depending on whether we consolidate or do it undrained, this may take an hour or 2 days, okay? If we have a very fine grained soil. So when let's say that this phase is done, and we still have sigma 3, let me put it here, sigma 3, sigma 3, sigma 3, sigma 3, all the way around. Still have this confinement applied. And now we're going to shear the sample. And to shear the sample, we're going to increase the stress in the vertical direction by increasing the load. And we do that typically by taking the bottom platen here, and then we push up against a resistance here, and then we have a measuring device on top of the piston. So we're going to increase the load Q, and so the stress, the additional stress that we generate is Q over A, where A is the cross-section area of the sample is A. So of course, action, reaction, we have the same thing at the bottom, Q over A, and then this altogether is going to form sigma 1. So be careful in some of the problems. I've seen some mistakes where people calculate sigma 1 equals Q over A. Don't forget sigma 3 because it's there. And so sigma 1 is sigma 3 plus Q over A. And we'll do some problem in a minute to exemplify this. So again, on the other side, we have sigma 1 right here. And because sigma 1 is different from sigma 3, the sample is subjected to shearing process. So this is the second phase, and this is called the shearing phase. Shearing phase. And this shearing phase, we, again, can do it drain or undrain. So this can be drained. That means that we open the valve here, and then the green line lets the water go through, or we can or we can do it undrained. Okay, we're going to use the letter D for this, and we're going to use the letter U for this. So in the end, we have a number of choices when we run those Traxel tests. We can do, you can combine this, you can do C, so types of Traxel tests. We can do a C-D test. So that means that the green line over there is open during the consolidation phase, remains open during the shearing phase, the water can drain out. We can do a CU test. That means that we consolidate the sample during the sigma 3 phase, but then we close the valve before we start increasing the load Q. We can do a UU test, where the consolidation part is done undrained. We just compress the water in the soil skeleton. And then we cannot do a UD test, because that would mean that we close the valve during the consolidation phase, and then we open it during the shearing phase. And if we did that, sigma 3 being still applied, we would actually consolidate the sample during the shearing phase. So this one is not possible. Okay. Typically, we will use the CD test and the CU test to obtain C prime and phi prime. I think I've called them C and phi in the previous lecture. And then this one, we typically use it to obtain the undrained shear strength of the soil. And different uses, the C and phi values, the effective stress shear strength parameters are used for when we want to do an effective stress analysis, and the undrained strength S sub U is when the loading is rapid in materials where there is no time for drainage to take place, like in the original case of the Tower of Pisa, for example. So these are the types of analyses that we do, and as a result of this test, we get something that looks like this, where we plot a stress-strain curve. And this stress-strain curve will typically here we'll put sigma 1 minus sigma 3 divided by 2. And we'll see why this when we start talking about the Mohr circle. And then here we put the vertical strain, because in the process of loading, the material is going to deform, and so under the load you have a compression here that's delta H, and you started with H0. So epsilon is the vertical strain, and so epsilon is going to be equal to delta H over H0. And this curve has different shapes, but you might get something that looks like that. And again, at the maximum value here, you find the value of sigma 1 minus sigma 3 divided by 2 failure. So that's typical stress-strain curve. The advantage is of the traxel test compared to the direct shear test is that we can get a modulus, we can get some information about the deformation properties of the soil in the early part of the curve. Remember, with the direct shear, we had the shear stress here, we had the horizontal displacement here. We did not measure the strain in the direct shear test, so we couldn't use that early part to define the properties. So that's a big advantage of the triaxial test. In addition to this, in this triaxial test, we can make some pore water pressure measurements. And typically we can put a sensor here, we put a sensor there. So right here, if needed, we can measure UW. That's a big advantage because if you want to obtain the effective stress, you know, sigma minus UW if it's saturated, or sigma minus alpha UW if it's unsaturated, then when you measure this, you can actually obtain the effective stress. And remember that when we want to plot, when we want to back calculate the equation parameters, you know, we're still looking at C equals C prime plus sigma minus alpha UW times tangent phi prime. Okay, this was the shear strength equation, and so this is sigma prime right here. This is the effective stress, sigma prime. All right. Let's do a problem looking at the results of a triaxial test and how we can obtain the properties, because in the end we're interested in this one and this one. If we have those parameters, whatever the problem is, we'll have to calculate this for that particular problem, and then we'll be in a position to find out what the shear strength is, and therefore what is the bearing capacity, what is the earth pressure, all the problems that are associated with these types of parameters and the shear strength of the soil. So the question then comes, how can I use the results of this triaxial test to be able to find the effective stress cohesion and the effective stress friction angle? We do this by Mohr circle analysis. So Mohr circle is what we're going to be talking about for the next while. So Otto Mohr, first of all, Mohr was somebody, Otto Mohr was a German civil engineer. And he did his work in 1882. Okay? And he showed, so 140 years ago, he showed that graphically there was a circle in this set of axes of tau versus sigma at the time. You know, we did 1882. We don't know about effective stress. Yes, Terzaghi, early 1900, came up with the concept and demonstrated how important the concept that was, and we've talked about this before. So he showed that in this set of axes, tau versus sigma, and sigma prime for us in soil mechanics, this circle would actually represent the state of stress that existed at one location. But I want to point out something important, and that's why I did not erase this, is that if you look at the set of axes where you have tau versus, and again, for us in soils, this will always be sigma prime. Then we have three principal stresses: sigma 3, sigma 2, and sigma 1. And so we really have three more circles. There's one right here, there's one right here, and then there's one right here. So really, for any point in the mass that is stressed, we'll have three principal stresses, and accordingly, three more circles. The reason we only have one more circle to deal with the triaxial test is because sigma 2 is equal to sigma 3. Okay? We don't change, we have sigma 3 this way, sigma 3 that way, and therefore this circle, because sigma 2 goes to sigma 3, then these circles disappear, and we have one more circle. So we have one more circle for the triaxial test. But just remember that in the general case, you have three more circles. All right, so how do we use this to obtain the values of C prime and phi prime in the shear strength expression? Well, we plot tau, shear stress, versus effective stress, sigma prime. And then we have sigma prime 3 here. And then we have sigma prime 2, sigma prime 1, sorry. And then we get the more circle at failure. Okay, so this would be the values at failure. You know the peak of the stress strain curve that I showed you, we take the peak of that line of that curve and we determine what sigma prime 3 failure, sigma prime 1 failure is, and what we apply are total stresses. This Q over A plus sigma 3, that's a total stress. So if we don't do the test, drain so slowly that there's no water pressure, we're going to have to measure UW and then subtract sigma 1 minus UW, sigma 3 minus UW with the alpha if we're in an unsaturated case. That's how we get these sigma prime 3 values, and we'll do a problem in a minute. And then you know that there is an envelope, which is this expression right here. S is a shear stress, and sigma prime is this. So this is a straight line, as I mentioned last time, and that straight line is defining the failure envelope. This is a circle that represents the state of stress of the sample at failure. So this line cannot be above the circle, because if it was above the circle, that could not be a failure circle. This line cannot intersect the circle because nothing can go over that line, since it defines the failure envelope. So by definition, this expression, this failure envelope, has to be tangent to the circle. But you say, well, okay, it's tangent. Is it this one? Is it this one? Is it this one? Is it this one? There are a lot of tangents to that circle. And that's why one circle is not enough. And typically, we'll have to do at least 2 triaxial tests to be able to define that failure envelope. So we might get a sample very close to the first one, and then do another test, and then we'd have another sigma prime 3 value, and another sigma prime 1 value, and then we'd get a second circle that looks something like this. And now that we had 2 circles, then we'd be able to put the failure envelope tangent to both circles, and we would be able to get C prime and phi prime in that fashion. So typically, and it's the same thing for the direct shear test. Okay, with the direct shear test, unless, and that's what's important to read the statement of the problem. If the statement of the problem says a sand sample is tested and so on, the minute it says sand, that means cohesion is 0, and then you know that you only have one unknown, phi prime, C prime is 0. So in that case, you would only need 1 circle or 1 triaxial test to solve the problem. But in the general case, you will need two triaxial tests. So let's do problem 926, page 236. So let me erase this. I guess I can erase this as well. I'll keep the equations there. All right. So problem 926, page 236. Page 236, here we are. 926. 2 CU triaxial test. So 2 CU triaxial test. So that means consolidated. We're going to consolidate the sample during the sigma 3 phase. We're going to open the line, and we're going to drain the sample, and then we're going to close the valve and increase the vertical load. Triaxial test, and we're going to increase the load, increase until we fail the sample. Are performed on a sample of unsaturated clay. All right, so that's the unsaturated. Clay. So that's the most difficult case, I guess. It's unsaturated, so we're going to have the water area ratio to contend with. And then clay, we cannot assume that C is equal to 0. So that's probably why the problem says 2, because we need 2 to be able to find the envelope. The results are as follows. So I'll repeat this. Test 1. And then test 2. And we're going to have to look at sigma 3, sigma 1. So sigma 3 equal, sigma 3 equal, sigma 1 equal, sigma 1 equal, and then we're going to have some information on the degree of saturation so that we can use that to estimate the water area ratio. And then the water stress is measured and is negative because the material is unsaturated. So the numbers are 20 kPa, 60 kPa, sigma 1, 190 kPa, 450 kPa. For sample 1, test 1, degree of saturation 60%. Second sample, 50%. And then water tension, 100 kPa, which is not very large. And then the second one, minus 300 kPa. You know, these values can go to minus 10,000. I mean, the water really can take a lot of tension. So here are the results at failure, right? So this is failure, 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 and failure. Okay, so these are the results that correspond to the top of that stress strain curve that I mentioned earlier. So the problem, the question is, calculate sigma prime 3 and sigma prime 1 at failure. So first question. We need to calculate for test 1 and test 2. We need to calculate sigma prime 3. So sigma prime 3 is going to be equal to sigma 3 minus alpha UW equal sigma 3, 20, minus alpha, we're going to estimate alpha by S as a ratio, so 0.6 times minus 100. Okay, so what is this? 80 kPa. Sigma prime 3 for the second case, same thing, 60 minus 0.5 times minus 300 equal, so minus minus, that's 150, 210. Okay. Good. I found the same thing as the book. All right. Then test 1, sigma prime 1. Test 2, sigma prime 1 at failure. Again, same thing. So I'm at 190 minus 0.6 times minus 100 equal, this is 60 plus, so 250. And then here I got 450 minus 0.5 times minus 300 equal, that's 150, that's 600. Okay, so I got 250 and 600, and so does the book. That's good. So now we have the results of these stresses at failure. Draw the Mohr circle at failure in the tau versus sigma prime center axis. So we're going to do that. Here is the tau, shear stress, versus sigma prime, set of axes. And we got numbers that go all the way to 600. It looks like the largest value. So we're going to be able to go from 0 to 600 right here in kPa. So it's going to be 300, 200, 100, 4, and 5. So 200, 400, 600, sigma prime in kPa. Always put label the axes and put the units on it. Again, you have to have the same scale on the vertical axis, 0, 200, 400, with tau in kPa. Now remember the story, if you don't put the same scales on the two axes, you will not get a more circle, more potato or whatever, but oval shape. So make sure you have the same scale in both directions. All right, let's put our more circle. We've got 80 for sigma prime 3, which is about here. And then I've got sigma prime 1 at 250. This is 300, 250. Here is circle number 1. And then circle number 2. Test 2, sigma prime 3, 210. Right about here. And then circle number 2 at 600. Right here. So second circle is right here. And now we have the two circles. These are circles of the test at failure. So therefore, I can use a tangent to both circles, and I can do this, and then find the common tangent. Well, sort of. Tangent to both circles, and then that's going to give me C prime and phi prime. And so that's a graphical solution to the problem. And then you would have to measure C prime on the scale, and this is why you need a protractor for the final exam, because you're going to have likely a problem like this, and you're going to have to measure this angle and that, and to do this type of problem. So that's how we use the triaxial test to obtain the shear strength parameters C prime and phi prime by plotting it always against the effective stress on the horizontal axis. Now, I would like to address the, in the time that I have left here, I would like to address the issue of how do you find the stresses on the plane within the triaxial test or the direct shear test or any test that you run in soil mechanics. And that requires, and I'm going to, and you can do this a number of ways. One of them is called the pole method, and that's a method that I kind of like. So I want to cover this method, but you may have learned it in stress analysis and other classes, other ways, and that's fine with me as long as you understand what you're doing and you get the right answer. So the question we're asking now is how to find stresses on a chosen plane in a soil element. In And I say soil element because the triaxial test basically represent an element of soil. So that's the question, and the solution that I would like to propose to you is called the pole method. P-O-L-E. Nothing to do with the folks from Poland. The pole is just the name that we give to the point, the special point on the Mohr circle. All right, so this pole method requires, to be able to apply that pole method, you have a number of steps, and I want to go through those steps, and then I'm going to use two examples to help you understand what those steps are all about. So step one, find a plane where the stresses are known. Two, find the corresponding stress points on the Mohr circle. Three, draw a line through the stress point parallel to the plane. So I'm going to actually give to find a plane, we'll call it P. All right, plane P, where the stresses are known. Find the corresponding stress point M on the Mohr circle. Draw a line through the stress point M parallel to the plane P. Okay. This line intersects the circle, the Mohr circle, in 2 points. 2 points. The stress point and the pole. Okay? Well, that's the property of the pole. Now this pole is a unique point on the Mohr circle. The plane can change, the pole doesn't. So once you found the pole, then you know where it is. It's not going to change. So that's how you find the pole. So finding, here, let's put it this way, finding the pole. Once you have the pole, so the second part is once you have the pole, you can find the stresses on any plane within the soil element. So how do you do that? One, given the plane direction, and I know this is a lot of do this, do this, do that. You will understand a lot better when we start doing those practice problems. Given the plane direction, draw a line through the pole parallel to the plane where the stresses need to be found. Two, that line intersects, that's the same property as before, the circle, the Mohr circle, in 2 points. The pole, obviously the pole because you drew the line through the pole. And the other one is the stress point and the stress point. And once you have the stress point on the Mohr circle, then you know the coordinates of that stress point are the shear stress and the normal stress that actually act on that particular case. So I don't have enough time to complete this, but let me do one brief example and we'll come back on this for the next lecture. Let's say that I have a Traxel test where I have sigma prime 3 and sigma prime 1, and here is tau versus sigma prime, and so I have sigma prime 3, sigma prime 1, here is the Mohr circle, all right? And so sigma prime, so this is going to be sigma prime 3, and this is going to be sigma prime 1. And I say, all right, I'm considering, it says to find the pole, find a plane where the stresses are known. Well, on this plane here, I know that the stresses are sigma prime 1 and 0. So this is the point that corresponds to that particular plane right here. And then it says, find the corresponding stress point on the Mohr circle. So that one is here. Draw a line through the stress point M parallel to the plane. So I'm going to draw through this point, I'm going to draw a line that's horizontal. Okay? That line is right here. Okay? This line intersects the Mohr circle in 2 points, the stress point and the pole. So that line intersects the circle in 2 points, the stress point and the pole. So therefore, the pole is right here. Okay? I could have done it using the other plane where I know what's happening. On this plane, the stresses is sigma prime 3 and 0 shear, and the plane is vertical. So I apply number 2 in red over there, find the corresponding plane, point on the Mohr circle, and then number 3 says draw a line through the stress point parallel to the plane. The plane is vertical, so I draw a vertical line. That vertical line intersects the circle in 2 points, the stress point and the pole. But because it's tangent, then those 2 points are the same. And so again, I confirm that the pole is right here. And then we'll see next time how I can use the pole to find stresses on any plane within the Traxel test, direct shear test, find principal stresses and so on. So we'll see you next time.